Hi, everyone. It's the last lecture. And so I have one more family of reactions to talk about, and that will do it for the term. But probably thinking a lot about Wednesday and the final exam. So just to remind you that the final exam is Wednesday, 9 to 11 a.m. And I posted study guide to the final on the course website. This is all under the tab called Final Exam. I also posted a practice exam, also under Final Exam, and I'll be posting the answers today. If anyone is interested, I have extra office hours, and that will be tonight, Monday, 7 p.m. to 8 p.m. in case you'd like to tune in and have any questions for me about anything. And please look at the study guide because people have asked me, well, what mechanisms do we need to know and what do we need to, like I always do, I'm telling you on the study guide exactly what you need to know and be able to do. So look at that study guide. It also has instructions for what to do if you miss the final and incompletes and all of that other stuff. So please check that out if you would. Okay, extra office hours tonight in case you have any questions about anything. Tomorrow, there's no lecture. But I asked the discussion leaders to have a final exam review during this time, during the lecture time, and I hope they have been in contact with you about what their plans are. But you have discussion, / review. Tuesday, that's tomorrow, 9 a.m. to 11 a.m. Right, I asked the discussion leaders to have a review during that lecture time. All right, so want to get into the final family of reactions today. But first, let's look at some pictures. All right, we've been talking about nucleophilic substitution, SN1 and SN2. And I wanted to point out that SN2 reactions are happening inside your body, inside a physiological system all the time. Probably the most preeminent one is the methylation of an oxygen, nitrogen, or a sulfur atom by S-adenosyl methionine, which is abbreviated SAM. And this is a substrate in a biological SN2 reaction. So the substrate, that's the compound that bears the leaving group. And we confined our discussion of leaving groups to the halides. Fluorine, although it never is, fluorine, chlorine, bromine, and iodine. But you have very little of this inside your body. Those are laboratory substrates. In a physiological system, the substrate, or one of the most important substrates for an SN2 reaction, is this guy, SAM. And if you look at this picture here, you see that this methyl group here on the positively charged sulfur, that's what's going to be attacked by the nucleophile. The rest of this molecule is all leaving group. So this molecule has evolved over billions of years And its leaving group is not any of the halides. That's more appropriate to a laboratory setting. But instead, the leaving group is this gigantic, well, there's an adenine residue. If you've studied DNA and RNA, you're familiar with adenine. This is ribose. And this is a methionine. This is an amino acid. So this is quite a molecule here. It has an amino acid stuck to a sugar, stuck to a DNA base in it. But all of this is leaving group, and the nucleophile is going to attack this methyl carbon. It's primary. And one of the interesting reactions, SN2, biological SN2 reactions in which SAM participates, is the biosynthesis of adrenaline. Now, I'm thinking maybe Wednesday at 9 a.m., there may be a lot of adrenaline flowing out there. Well, adrenaline's an interesting molecule in that if you had all of the adrenaline you ever needed in your body, you'd be dead now, because adrenaline, a high concentration of adrenaline, has some very harmful effects. It increases your heart rate, it depresses metabolism, it increases blood pressure. If you had all of the adrenaline you ever needed in your body at one time, you'd be dead now. Instead, what you have is a reservoir of norepinephrine or noradrenaline, which looks just like adrenaline, except norepinephrine has two hydrogens on a nitrogen atom, whereas adrenaline has a methyl group and a hydrogen. SAM puts the methyl group on norepinephrine, converting norepinephrine to adrenaline. So every time in a biological system you see a methyl group on a nitrogen or an oxygen or a sulfur atom, lots of times that methyl group got there by a biological SN2 with SAM as the substrate. And in this case, the nitrogen atom of norepinephrine is the nucleophile. Okay, so just some more examples. For example, nicotine. I see a methyl group on a nitrogen atom. How'd that get there? It was a biological SN2 reaction in which the SAM delivered that methyl group to that nitrogen atom. Oh, and there are many, many other examples. Here's another example, physostigmine. I see a lot of nitrogen with a lot of methyl groups on them. How did they get there? SAM was the substrate, and those nitrogen atoms were the functioned as the nucleophile. So this physostigmine, this is an anti-glaucoma drug, but it was discovered by Percy Julian, who is one of the pioneers in discovering medicine from natural sources like plants and animals, analyzing them, figuring out, if possible, how they work, and then synthesizing them in the laboratory. So that was one of Percy Julian's big contributions to organic chemistry. He was a pioneer in this field. And so this is a judicial ordeal poison. So he was visiting someplace in Africa. I can't remember whether it was Kenya or Tanzania. And the people that he was studying, if they had a beef with another member of their society, instead of getting a lawyer, what they would do is they would eat the berries and the leaves of this plant, Physostigma venenosum, and it's deadly. And whoever survived eating the berries and the leaves of this plant won the lawsuit. So that's a judicial ordeal. And he was interested in this compound because he noticed it had a big effect on the eyes of the people that were engaged in the judicial ordeal. And he collected the sample and extracted this compound, which is still used as an anti-glaucoma drug. So there's lots and lots of biological examples of an SN2 reaction. Here's another one. where you have a coil of DNA, and you know, if you've studied DNA, you have these NH2 groups in the DNA. This molecule over here, I see a chlorine leaving group on a primary carbon. This is mustard gas. This is a chemical warfare agent. And the mechanism by which mustard gas and other various chemical or this chemical warfare agent works is that the nitrogen atoms of DNA, those are the nucleophiles, this carbon atom, primary carbon atom that has this Cl leaving group, that's the substrate. And so there's a reaction in which the mustard gas spans a length of DNA, and now it has chemically modified that DNA. That DNA is no good anymore. And if that DNA is coding for some of the enzymes that are involved in metabolism, then, you know, within maybe about an hour or so, you're dead after having been subject to a mustard gas attack. So there's another SN2 reaction where the nucleophile, the nitrogens, have replaced that chlorine leaving group on the primary carbon. Okay, so lots of examples of biological SN2, and also lots of examples of SN2 in which, in the medical world. Okay, last little family of reactions is the elimination reactions. And elimination reactions, this is what happens when the conditions for substitution are not favorable. Happen when substitution is unfavorable. There are two elimination mechanisms. There's the E1 and the E2. The elimination reactions, these compete with substitution. So you go into the laboratory and you think you're running a substitution reaction, you think you're running an SN2 reaction. Well, that may or may not work. But if the conditions for SN2 aren't favorable, the reagents, the reactants aren't just going to sit there doing nothing. They're going to do an elimination reaction. So frequently, when you're trying to run a substitution reaction, you get some elimination product anyway as a byproduct. So substitution and elimination compete. As I said, there is the E1 and the E2 mechanisms. And it would be nice if E1 competed with SN1 only. And it would be nice if E2 competed with SN2 only. But the truth is so messy. And we'll unpack and explain all of these things as the elimination story unfolds. Okay, so let's look at a situation where substitution is unfavorable. Okay, and this is where elimination is going to happen. So for example, I could have something like this. Okay, that's a secondary alkyl halide. And now I want to react that with a nucleophile. But the bad, unfortunate choice of nucleophile here is this tertiary butoxide. And we've talked about this tertiary butoxide, and we mentioned that this is a sterically hindered base and a very bad nucleophile. And why is it a bad nucleophile? Because it's sterically hindered. In the SN2 reaction, the nucleophile has to get in and push the leaving group out. the nucleophilic atom on this tertiary butoxide, the oxygen is dragging behind it this massive chicken foot. And so it is sterically hindered. It can't get in there to push the leaving group out. There's just too many methyl groups and there's too many obstructions in the way. Okay, but these guys aren't just going to sit there doing nothing because they can't do an SN2, because we have to remember that this is still a base and it's a powerful base, so that it's not going to function as a nucleophile. It can't. It's too bulky. It's too crowded to function as a nucleophile. It's not just going to sit there doing nothing. It's going to do an elimination reaction. Okay, so most popular. So what happens is elimination, and the products of the elimination would be that. We'll explain how all of these happen in a while. And so here we get E2 elimination, right? Most popular, wrong answer is this guy down here below. Most popular, wrong answer, the SN2 product. Impossible. The nucleophile is too crowded. It can't get in there to push the leaving group out. So that although it looks like all of the fixins, all of the ingredients for SN2 are there, it will not be an SN2 reaction. It will be an E2 reaction. Okay, so let's talk about the E2 mechanism. Okay, so we have a substrate, just like in SN2. We have a substrate, and up here I'm going to put X. That's the leaving group. We're just talking about halide leaving groups. The halide is on an sp3 carbon, and the carbon that bears the leaving group, we'll call that the alpha carbon. The carbon next to the alpha carbon, that's the beta carbon. And the beta carbon has a beta proton on it. And the beta carbon must also be sp3 hybridized. So far, this looks, this substrate, it looks like something that could undergo the SN1 or the SN2. Okay, but under certain conditions, it will not undergo SN1 or SN2. It's going to undergo the E2. Okay, so that's the substrate. The other actor in this drama is a base, right? And many bases, most bases have a negative charge, and they all have an electron pair available for bond formation. So the ability of the base to function as a nucleophile has been defeated, right? There's something wrong with the substrate, or there's something wrong with the base. We'll unpack all of that in a second. But what I'm saying is the base cannot function as the nucleophile. It's not just going to sit there doing nothing. It's going to do an E2. And in the E2 elimination, the base takes this electron pair and removes the beta proton from the beta carbon. The electrons that were keeping the beta proton on the beta carbon rush up in here to make a new carbon-carbon double bond. So you see, this is a way of making an alkene from an alkyl halide, and the alkyl halide departs. So remember how the SN2 was one step? The E2 is also one step, where base is removing the beta proton, a new carbon-carbon double bond is forming between alpha and beta, and the leaving group is leaving all in one step. So we can picture the transition state for the E2, where that beta proton is being yanked off. It's being yanked off by the base. A new carbon-carbon double bond is forming between the beta carbon and the alpha carbon. And the leaving group is leaving. So I'm dotting all of these bonds, showing that these are bonds in the process of being formed and being broken. All right, so there's the transition state. I'm going to put that all in brackets. I'm going to put a double dagger up here. What about formal charges? This base is losing its negative charge. So at the transition state, it has a partial negative charge. This halide is acquiring a negative charge. So at the transition state, it has a partial negative charge. Okay, the products of the reaction, a new double bond between alpha and beta. Right, so synthetically in the laboratory, this would be a way of making a carbon-carbon double bond. We know another way of making a carbon-carbon double bond, and that is by reduction of an alkyne. Hope you were able to check in on that makeup lecture. The other products of this reaction would be X minus, that's the leaving group. It departed with its pair of electrons, and the base is protonated. Okay, so if we go to that previous example that I gave you, we saw we had an alkyl halide like so. There's the alpha carbon, there's the beta carbon, there's the beta proton. The base that we used was tertiary butoxide. Tertiary butoxide removed the beta proton. The electrons that were holding the beta proton onto the beta carbon rush in to make a new carbon-carbon double bond, and the leaving group leaves, and all of this happens in one step. Our products are a new alkene bond between what used to be the alpha carbon bearing the leaving group in the substrate and the neighboring carbon, which is this beta carbon. The other products of this reaction would be chloride minus and the protonated tertiary butoxide, its conjugate acid. Okay, so that's the E2. That's an E2 elimination. It happened because substitution couldn't happen, because the nucleophile is too crowded to get in there to push the leaving group out. Okay, so more detail about the SN2, more detail about the E2 mechanism, and that is its stereochemistry. The beta hydrogen and the leaving group must be anti to each other. All right, and so this is a consequence of the one-step character of the E2. Remember when we were studied SN2, that was a one-step mechanism. That had all kinds of consequences. One of them was backside attack of the nucleophile on the substrate carbon. If the leaving group were on the front of the molecule, the nucleophile has to come in from the back. If the leaving group is in the front of the molecule, the nucleophile can't come in from the front because that's a sterically hindered situation. Well, in the E2 elimination, we have the very same requirement, in that we're looking for the minimum amount of steric hindrance. If the leaving group is going out the top of the molecule, the base is going to want to come in from the bottom of the molecule. And this is the favored geometry, the required geometry for the E2 elimination. So we can put that, we can illustrate that using a Newman projection. All right, so here is the alpha carbon in the front. That bears the leaving group. The beta carbon is behind the disk. It's hidden by the disk. We can't see the beta carbon, but we can see everything bonded to the beta carbon. There must be a proton on the beta carbon, and these must be anti to each other. That is what is required. And so the base comes in, removes the beta proton, new double bond forms, and leaving group leaves. All of this happens in one step. And what we're left with is an alkene. So we could represent the alkene by a Newman projection that kind of looks like that. But now the implication, there's a double bond there. And the other products of the reaction would be X minus and the conjugate acid of the base. Okay, so this is a stereochemical requirement. And why it's required is because the eclipsed transition state simply too crowded, right? We would have the alpha carbon here with the leaving group leaving. We have the beta carbon over here with its beta proton. And the base, the big bulky base, something like this, trying to pick up this proton here. Just too crowded. You see how I put that big T-butyl chicken foot up there on the top? That's going to get into the way of the leaving group as it leaves. So the transition state and the stereochemical requirement for the E2 is that the beta proton and the leaving group on the alpha carbon must be anti to each other. Okay. Substrate in E2, any a primary, a secondary, a tertiary, they can all undergo the E2. Most of the decision of whether you're going to get E2 or SN2, in fact, lies with the nucleophile / base rather than with the substrate. So any kind of substrate can take part in the E2. Finally, the product of the E2. We get the most substituted alkene. So we would get the tetra-substituted alkene in preference to the tri-substituted alkene, in preference to the di-substituted alkene, in preference to the mono-substituted alkene, in preference to the unsubstituted alkene. So there's a tendency to form the more thermodynamically stable, more substituted alkene, but the truth is so messy, right? But the beta proton and the leaving group X, they must always be anti, right? So we're not going to get the most substituted alkene if it violates the anti-transition state. We get the most substituted alkene, but we have to satisfy this requirement. And there's another but, is that bulky, sterically hindered bases, these give the less substituted alkene. But once again, the beta hydrogen and the leaving group must be anti to each other. Okay, and so said a lot here. So let's just do some problems here and try to flesh out some of these ideas about the E2 elimination. Okay, so for example, we would have something like all right, so I'm telling you right now that that's an E2 elimination. It's going to be an E2 elimination. We'll talk about why it's an E2 elimination later. Okay, that's an E2 elimination. Draw the structure of the major product. Okay, so how does an E2 elimination work? Is that it puts in a new double bond between alpha and beta. Right? So the alpha carbon is the carbon that bears the leaving group. The neighboring carbon is the beta carbon. This guy has 3 beta carbons. That's the maximum number. And so we're going to get a new double bond between alpha and beta, but always remembering that the beta proton and the leaving group must be able to have an anti-relationship, and then remembering that the most highly substituted alkene will be the major product so long as the geometrical requirement of the beta proton and the leaving group being anti is satisfied, and so long as the base is not a bulky base. Well, this is not a bulky base, so we don't have to worry about that. What we do have to worry about is that we have several different products here are possible, and they will all form. So we could put the new double bond between the alpha carbon on the left, the beta carbon on the left and the alpha carbon. So that could be one of our products, right? I just drew a double bond between alpha and beta. That's what happens in an elimination. Then I could also draw another product in which I'm going to sling that double bond up. That's a new double bond between the alpha carbon and the beta carbon. But I noticed that these two guys are the very same structure. All that has to happen is rotation about this carbon-carbon single bond. So this aren't two different molecules. They're the same. They're identical. Okay, and then the other product here is going to have the double bond between alpha and beta. Oh, like so. All right, that's going to be our major product, right? This is going to be the major product. Why? Because this is tetra substituted, whereas these other guys were di substituted. We're going to get the most thermodynamically stable alkene, which is the more highly substituted alkene. That's nothing new, right? What's the most stable kind of carbocation? Or one of them is tertiary, more substitution. What's one of the most stable kinds of radicals? Tertiary, more substitution. It's the same with the alkene for the same reasons. More substitution stabilizes that double bond. Okay, now I want to address the issue about the geometry, the anti-geometry that leads to this major product. Okay, so if we look at this and we try to draw a Newman projection, what I'm going to do is I'm going to put the beta carbon in the front, right? And so the beta carbon is a fishtail. And I'm going to put the BR, the alpha carbon is in the back. And so I see that, yes, the alpha, the leaving group on alpha and the proton on beta can be anti to each other. So that is going to lead to this. All right. So these are all methyl groups there. And what about this guy over here? Well, now once again, I'm going to put the alpha carbon in the front because that's the one I'm interested in. And the beta carbon in the front because that's what I'm interested in. So that's one of those carbons in that methyl group. All right, the alpha carbon is hidden behind the disc. That alpha carbon has a methyl group on it and it has a fishtail on it. Can the beta proton and the leaving group on alpha, can they be anti to each other? They can. So this is the transition state that is going to lead to these products. So it's so you're just getting a new double bond between alpha and beta. All right, so let's try another one. All right, this one's a little trickier, or a lot trickier. I'll make things easy for you by telling you it's an E2 elimination. And what would be the major product here? All right, so there's the alpha carbon. This guy has beta, 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 3 betas. An elimination puts in a new double bond between alpha and beta. So I see several possibilities here as far as E2 is concerned. I could sling the double bond to the left. I could sling the new double bond down, and I could sling the new double bond out. Okay, there are the 3 possible elimination products. And once again, I notice that these guys are identical. So it's not really too different. These aren't 2 different molecules, they're the same. And so I get 2 products. But which one would be the major product here? Well, the major product here is going to be the less substituted alkene. This is di-substituted. And this would be the minor product, tri-substituted alkene. All right, and so this is one of the things we have to watch for, is that when we use a bulky, sterically hindered base, we're going to get the less substituted alkene as the major product. Why? Because in order to pick off the beta proton down here at 4 o'clock and the beta proton over here at 12 o'clock, it's just, the base here is just too big and bulky to be able to get in there and remove those protons rapidly. Instead, what the bulky base does is it goes for a proton on the exterior of the molecule, a more sterically accessible proton. Because of its huge steric bulk, it's just going to be easier to grab a proton from the periphery of the molecule than somewhere on the interior. So that's why a bulky base gives us the less substituted product. And once again, could that beta hydrogen and the leaving group, could they be anti to each other? Because if they can't, then we won't have an E2. Well, one of the skills we know about is translating a chair to a flat drawing and vice versa. And I see here in this chair conformation, I see that, yep, the leaving group Br and the beta proton, they can be anti to each other. And so that is the transition state that is going to lead to this formation of this double bond on the exterior, on the outside of this molecule. Okay. Another example. Um, all right, this is also going to be an E2. Draw the structure of the major product. Okay, so tell me in the chat here, major product is the double bond. Am I going to swing the double bond to the left, or am I going to swing the double bond to the right? The carbon that bears the leaving group, that's the alpha carbon. The neighboring carbon is the beta carbon. The E2 elimination puts in a new double bond between alpha and beta. Tell me in the chat here, is the new double bond going to be to the left, or is it going to be down in the major product? Okay, what if I said most popular wrong answer is to the left and the correct answer is down? Sorry about that. Okay, so yeah, the major product will be this 100% and double bond swung to the left 0%. Can't happen. All right. And so why is this? Because we always have to remember that when we're dealing with the E2 elimination, the beta proton and the leaving group must be anti. So if I rewrite this molecule, giving you all kinds of detail, right, I would end up with something that looks like that. The Cl is up. The H on the beta proton is up. How could that ever be anti? Anti means one is up and one is down. If we wanted to translate this into a chair conformation, we would see Cl is up here, right? I'm making it axial. The beta proton is equatorial, and that methyl group is axial down. Okay, what does the other chair look like? All right, the other chair, the Cl used to be axial, it's now equatorial. The hydrogen used to be equatorial, it's now axial. The methyl group used to be axial, it's now equatorial. And once again, the Cl and the beta proton that makes the double bond on the left, they can never be anti. These are gauche. These are gauche. So it's not just a matter of slinging that new double bond into the most substituted position. You also have to keep in mind that there's a stereochemical requirement for the E2 elimination, where the leaving group and the beta proton have to be anti. And elimination in this direction back here, that just can't happen. Okay, so now let's look at elimination in the direction, in the correct direction. Okay, so once again, hydrogen, methyl group, axial Cl, equatorial H, axial H. Yep, there they are. They're anti to each other, and they can undergo the elimination, and that's why that double bond is the less substituted double bond, because creation of the more substituted double bond here is impossible because it violates the stereochemical requirement for the E2. Tricky, huh? Okay, so let's talk briefly about the E1. E1, this is a carbocation mechanism. Rearrangement are possible. The major product, this is going to be the most substituted alkene. It doesn't have the stereochemical requirement of the E2. So the E1 is a carbocation mechanism. So here's our beta carbon. Here's our alpha carbon. In the E1, just like in the SN1, the first step is departure of the leaving group to leave behind a carbocation. There's our beta carbon. Here's our alpha carbon. There's the carbocation, right? And this guy may or may not rearrange. Okay, then the base comes in, right? And this guy, there's free rotation here. So there is no, the leaving group is gone. The reason the E2 transition state is the way it is because the base doesn't want to crash into the leaving group. But the leaving group's gone already, so this doesn't have that geometrical requirement. Base comes in, removes the alpha proton, you get the new double bond. And once again, we see a new double bond between alpha and beta, providing that rearrangement didn't happen. And the other product is the H base. Okay, and here, we're just always going to get the most substituted double bond as the major product. All right, so E2 elimination could be maybe something like this. Sorry, E1 elimination, and let's see, let's use water. And I'm telling you, it's an E1. So draw the structure of the major product. It's E1. So that means the first step is the removal, departure of Cl minus. We get this carbocation, right? Uh-oh, this is going to be able to rearrange from a secondary to a tertiary. So there's a rearrangement to a tertiary. And now this is our alpha carbon, there's our beta carbon, there's our beta carbon, there's our beta carbon. And so we have several possibilities here. Could eliminate to 2 o'clock. We could eliminate to 6 o'clock. And we could eliminate to 4 o'clock. And once again, these two guys are identical. And they are tri-substituted. So that would be the major product. This guy is di-substituted. We'll get some of it. We'll get some di-substituted product, but not very much. Okay, I'm going to take my traditional break now. And then when I come back, we're going to wrap up looking at the competition between substitution and elimination. But could you please, during the break, could you please log on to this website? This is the course evaluation, right? And if you could fill that out, during our break, I would appreciate it. So this says bucampuslabs.com course eval with 2 E's in there, course eval. If you don't want to do this right now, you can do it on your own time, but please fill out a course evaluation if you would be so kind. Okay, so my computer says 9:52. I'll be back at 10:02. The previous page. Let's see. I don't want to lose this course evaluation info, so that's the best I can do for right now. A little bit higher. I'm back, everybody. So now when we're talking about substitution and elimination, everything's a crisis because we have to decide what is the major product going to be? Is it going to be an elimination product or is it going to be a substitution product? So that's what I would like to talk about now. All right, and I'm dividing this up into the nature of the substrate, whether it's a primary substrate, secondary substrate, or what. All right, so beginning with a primary substrate, we're trying to figure out, is the major product going to be the substitution product or the elimination product? First little decision here is we have to ask ourselves, is it beta branched? Is it a beta branched primary? Okay, so now what beta branching means is over here, let's see, we'll draw a naive little picture of a tree, right? This is the trunk of the tree, and here's a branch, right? Trunk and branch. Okay, so now translating this into an organic molecule, we would have the leaving group there, right? And this could be the trunk. The carbon that bears the leaving group, that's the alpha carbon. And now on the beta carbon, I'm going to put a branch. See, that's beta branching. Something like this, that's all trunk and no beta branches. I could have a branch over here, but that's not a beta branch, so that's no beta branching. All right, so that's what you're looking for. First of all, is it beta branched or isn't it? And the reason that this is important is because in an SN2 reaction, and remember, we never see SN1 on a primary substrate. So this, if we're going to get any substitution here at all, it's going to have to be SN2. And in the SN2 reaction, the nucleophile has to push the leaving group out. If I'm junking up the neighborhood of the alpha carbon with fishtails and chicken feet and all this other stuff, that's going to make it hard for the nucleophile to get in there to push out the leaving group. Okay, so is it beta branched? So let's say yes. Let's say no. All right, if it's beta branched, then the next thing that we would look for would be, is the nucleophile a strong base? Question. And if it is, we'll get E2 elimination. The carbon that has the leaving group is too junked up for the nucleophile to get in there and push the leaving group out. But the nucleophile is also a strong base, so it's not just going to sit there doing nothing. It's going to do an E2 elimination and not a substitution. All right, so now this little decision, this little question here has a new some new vocabulary, strong base. And I hope you got to tune into that makeup lecture where I talked about what a strong base is and what a strong base isn't. So let me just make a little summary of this. Strong base has a conjugate acid of pKa greater than or equal to about 14. Okay, so that's what a strong base would be. Let's look at some examples of stuff that are strong bases and stuff that is not a strong base. So hydroxide, is that a strong base? Oh, it is, because the pKa of its conjugate acid, which is water, is 16. Okay, methoxide, is that a strong base? It is, because the pKa of its conjugate acid, methanol, is 17. The alkynyl anion, is that a strong base? It is, because the pKa of its conjugate acid is 25. So all of these are strong bases. And how can you identify a strong base? The pKa of its conjugate acid is greater than 25. But now something that is not a strong base would be phenoxide. The pKa of its conjugate acid is 10, right? That's below this threshold. This is a base, no doubt about that, but it's not considered a strong base. And a strong base is different from saying that something is a strong base, or saying that something is not a strong base is different from saying that something is a weak base, right? This isn't really a weak base, it's just not a strong base, right? There's a continuum. Something else that is not a strong base would be maybe something like this. This bis alpha carbon that has that negative charge tucked between two carbonyls, its conjugate acid, which would look like that, also has a pKa of about 10. So this is not a strong base. It's a base, but it's just not considered a strong base. Okay, so that's how we can clarify the use of this term here, strong base. Primary substrate, beta branching, yes. Nucleophile a strong base, yes. You're going to get E2. The nucleophile can't get in there to push the leaving group out. All right, so here we need a no. Okay, and so the substrate wasn't beta branched. Okay, so next thing we would look for over here would be sterically hindered base. If yes, we're going to get E2. And if no, we're going to get SN2. And over here, we're going to get SN2. Okay, and so we talked about what is and what is not a sterically hindered base, right? And so I'm just going to put that in this little box down in here, right? The hindered bases. There are others besides the ones that I'm going to list here, but these and bases like these are considered sterically hindered. That tertiary butoxide is sterically hindered. This diisopropylamide, that would be sterically hindered. You see how that negatively charged atom has been junked up by all kinds of fishtails and chicken feet and so on. And then the triphenylmethide, that would be a hindered base as well. You have this carbon atom surrounded by 3 benzene rings. Okay, so that's what we're looking for to decide whether we're going to get substitution or elimination with a primary substrate. Is the substrate beta branched? Yes or no? Is the nucleophile a strong base or a hindered base? Yes or no? See, so the thing is that beta branching, that is an enemy of substitution. Sterically hindered bases, those are enemies of substitution. So that when the conditions aren't right for substitution, elimination is going to take over. Okay, so that was for a primary substrate. The other ones are easier to deal with. Secondary substrate, nucleophile, a strong base. Question, yes, get E2. No, this is going to be either SN2 or SN1. It's hard to tell, but it's going to be substitution rather than elimination. So that's pretty simple there. All right, for a tertiary substrate, once again, it's going to look exactly the same. Nucleophile, a strong base. If yes, going to get E2. If no, well, it's a tertiary substrate. We never see SN2 on a tertiary substrate, so this is going to be SN1. So you see, for a secondary and tertiary substrate, what you're really looking for is whether that nucleophile slash base is strong or not. If it's a strong base, a secondary and a tertiary substrates are just too crowded up for the nucleophile to get in there. It's not going to sit there doing nothing. It's going to function as a base and promote an elimination. Okay, want to do some problems where we're testing out these little flow charts. But before we do that, one of my favorite things to say is the truth is so messy. Remember, substitution and elimination are enemies. When substitution can't happen, elimination can happen. But there are some, I want to point out that there are some examples that seem to contradict everything I've just said, but when you think about it from a mechanistic and fundamental point of view, they make sense. Okay, so here I have a primary substrate, and here I have a sterically hindered base. So let's go back to our little flow chart and just apply this flow chart in an uncritical, robotic way, which is wrong. Okay, is it beta branched? Well, it looks like it is, right? There's the alpha carbon, there's the beta carbon. I see a bunch of stuff on the beta carbon. Is it beta branched? Yes. Is the nucleophile a strong base? Yep, the pKa of the conjugate acid of this is 17. So just robotically, uncritically, without thinking of what I'm doing, just using this flow chart, elimination would be the major product. Elimination puts a double bond between alpha and beta. So that should be the product. See anything wrong with the product? Tell me in the chat if you see something wrong. Right, I just followed the flow chart robotically and uncritically. Oh, I see something with 5 bonds, right? So that flow chart is telling me elimination, but the flow chart is wrong because substitution and elimination are enemies. This guy can't undergo elimination. So what is going to happen is substitution is viable here. Elimination happens when substitution can't. What happens when elimination can't happen? Substitution does. So this is going to be SN1. Whoops. It's going to be SN2. And I'm going to get that SN2 product. right? Flowchart be damned. And the reason this works is because elimination can't happen. Okay, maybe someone is asking me, can you explain how to determine alpha and beta? Alpha is the carbon that bears the leaving group. Beta is the next door carbon next to the alpha carbon. Alpha is the carbon with the leaving group, and beta is just the neighboring carbon. So elimination can happen. It's not SN1 because SN1 uses weak neutral nucleophiles or halides. And this is not a neutral nucleophile, and it's not halide, so it's going to be SN2. But now, if I change this up a little bit, and now do that, plus, oh, now I see elimination can happen, and it will. Plus, see, elimination can happen because there's a proton over here on the beta carbon, and I'm not getting something with 5 bonds. So this was just a robotic application of this. Secondary substrate, yep. Nucleophile, a strong base, yep, E2. So that flow chart is useful, but you have to be careful how you apply it. You just can't be, uncritically using that flow chart. You always have to remember that substitution is the enemy of elimination, and elimination will take over when substitution can't. All right, so let's do some problems. Where we're trying to predict what the heck is going to happen. Okay, predict the product. The slide is headed substitution versus elimination, right? So what's going to happen here? Is this going to be substitution or is this going to be elimination? Do I still have chat on here somewhere? Yeah, I do. Where is my chat? More? Chat. Yeah, tell me. Tell me in the chat. Substitution or elimination? Draw the structure of the major product. Anybody want to give it a shot? Is it going to be substitution or elimination? Oh, it's going to be elimination all the way. All right. So here's the alpha carbon. There's the beta carbon. This has beta branching. So let's go back to our little flow chart. For the primary substrate. Primary, beta branching, yes. Nucleophile, a strong base, it is. It's an alcohol. pKa of the conjugate acid is 17. So that is going to be elimination as the major product, right? This is a beta branched primary substrate with a strongly basic nucleophile. All right, so let's take this into the lab and let's see what we got. Yep, 62% elimination. We did get some substitution, 38%, but the major product was an elimination product. So are you seeing how to use that flow chart, right? Okay, let's try another one. So once again, tell me in the chat, substitution or elimination? Draw the structure of the major product. So is this going to be substitution or elimination for this one? Can't see the chat here. Wow, so much clicking. Yeah, this is going to be substitution because it's a primary substrate. Is it beta branched? It is not. Where's my flow chart? Primary substrate, beta branch, no. Sterically hindered base, no. SN2. So here the conditions were good for substitution, and substitution is the major product. Beta branching means there's more than one alkyl group on the beta carbon. See here, this beta carbon is here. There's only one alkyl group that's not branched. So beta branching means more than one alkyl group on the beta carbon. All right, so let's take this into the lab and let's see what we got. Oh, 92% substitution. But we got a little bit of elimination. Substitution and elimination always compete. Here, the conditions were good for substitution. The nucleophile could get in there and displace the leaving group. Okay, so now let's try this one. Okay, I'm not going to ask you to answer me in the chat because it's just too much clicking for me to look at the chat. So just decide in your own mind, is this going to be substitution or elimination? Major product. Okay, now this is secondary. Let's whip out our secondary flow chart. Is the nucleophile a strong base? Is Cl minus a strong base? Cl minus is the conjugate base of HCl, which is a very, very strong acid. A very strong acid is going to have a very weak conjugate base. So is this a strong base, Cl minus? Oh, not at all. It's an exceedingly weak one. So we have a secondary substrate. We have a nucleophile that's not a strong base. We're predicting that conditions are ripe for substitution, not elimination, right? Elimination is essentially an acid-base reaction. Cl minus is just a lousy, lousy base. If given the option between functioning as a nucleophile or functioning as a base, it's going to function as a nucleophile. Okay, so let's see what we actually got in the lab. Yeah, 82% substitution, a little bit, well, to 18%, some elimination, but our major product would be the substitution product. Yes, you're getting the hang of it? Okay, how about this guy? So that TBUO minus, that's tertiary butoxide, that's this guy here. Primary substrate, beta branching, sterically hindered nucleophile. What else could go wrong for substitution? Right, so there's no way this is going to be a substitution reaction. The beta branching makes it hard for the nucleophile to get in, to push out the leaving group. The nucleophile is sterically hindered. Everything is saying, arguing against substitution. So the product here we're predicting will be elimination. Yes? Okay, so let's see how we did. What do we actually get in the lab? Oh, we get elimination 100%. No substitution whatsoever, because tertiary butoxide is a terrible nucleophile. It's too sterically hindered, but it is a powerful base, and elimination is an acid-base reaction. Okay, try some more. Substitution or elimination? Well, that's going to be elimination as the major product, because this is a secondary substrate. It's difficult for the nucleophile to get into that crowded secondary position. The ethoxide is not just going to sit there doing nothing. If it can't get in if it can't get in there to push the leaving group out, it's going to function as a base and do an elimination reaction. So yep, we're predicting elimination as the major product. So let's see what our result was. Yeah, elimination is the major product, about 80%, and we did get some substitution, but the elimination prevailed. Okay, oh, this one's so easy. Is that substitution or elimination? Tertiary substrate. My cheat sheet. Tertiary substrate, strong base nucleophile, elimination. And I know we get 100% here because that tertiary butoxide cannot function as a nucleophile. So there's always this competition between substitution and elimination. And every time we're dealing with a substitution reaction, we have to take into account the nature of the substrate and the nature of the nucleophile and make sure that what we think is going to happen actually will happen, and that we haven't mismatched the substrate with the nucleophile. Okay, so let me look at what's going on in the chat here. Can the double bond be on either side because of symmetry? It can. How do we tell if it's a primary, secondary, or tertiary substrate? Is how many carbons are bonded to the carbon that bears the leaving group? Well, guys, that's it.